There is a star in our sky right now that is older than the universe itself. At least that's what the math said. And for years, astronomers had no answer for it. We have models for how stars are born, how they live, and how they die. Those models have been tested against millions of stars. They work almost perfectly. Almost. Because scattered across our galaxy and a few others, there are stars that look back at our equations and simply refuse to cooperate. Stars with elements that have no business existing. Stars built from two completely different objects. Stars so ancient they predate everything we think we know about cosmic time. These aren't theoretical. They've been photographed, measured, studied for decades. And in every case, they shatter something we thought was settled science. Let's start with the one that nearly broke astrophysics. About 190 light-years from Earth, close enough that on a clear night you could spot it with binoculars. There sits a pale, faint star in the constellation Libra. Scientists call it HD 140283. Most people call it the Methuselah star, named after the oldest man in the Bible. And when astronomers first calculated its age, the number that came back was 14.46 billion years. The universe is 13.8 billion years old. Read that again. The star appeared to be 660 million years older than everything. Older than time itself. Older than the Big Bang. That's not a rounding error. That's not a data glitch. That's a star telling physicists their entire timeline of cosmic history might be wrong. How do you even age a star? You measure its brightness, its temperature, which for HD 140283 clocks in at around 9,700 degrees Fahrenheit, and its chemical makeup. Old stars have almost no heavy elements because heavy elements didn't exist yet when the universe was young. The Big Bang produced hydrogen and helium. That's basically it. Every carbon atom in your body, every atom of iron in your blood, those were forged later, inside stars that lived and exploded before our sun was even born. So when you find a star with almost no metals, no heavy chemistry, you know it came from the very beginning. And HD 140283 is almost entirely hydrogen and helium. Its metal content is roughly 250 times lower than our sun's. That puts its birth date somewhere near the very dawn of the cosmos. The problem was the margin of error. Scientists had the age pinned at 14.46 billion years, plus or minus 800 million years. On the low end, that gets you to 13.66 billion years, just barely younger than the universe. But the central estimate was still impossible, and the astronomy world had to confront a deeply uncomfortable question. What if our timeline of the universe is wrong? Over the following years, multiple teams went back and reanalyzed the data. They refined the star's distance using the Hubble Space Telescope's most precise instruments. They reworked the models. By 2021, a revised estimate had narrowed its age to around 12 billion years, solidly inside the age of the universe. A 2025 asteroseismology study, which measures the subtle vibrations rippling through a star's interior the way geologists read earthquakes, landed on 14.2 billion years. Still technically within one standard deviation of being younger than the universe, but only just. Here's what nobody likes to say out loud. We haven't fully resolved the Methuselah problem. We've narrowed it. We've adjusted the numbers until they fit. But the reason a nearby star appeared older than everything still comes down to uncertainties in our models, our measurements of cosmic expansion, and possibly in our understanding of stellar physics itself. The universe's age is calculated largely through a number called the Hubble constant. And right now, two different ways of measuring that constant give two different answers. Physicists call this the Hubble tension. It has been unresolved for years. What if HD 140283 isn't wrong? What if it's pointing us toward a universe slightly older than we thought? That question is still open. Now let's talk about a star that contains another star inside it. In 1975, two physicists, Kip Thorne and Anna Zhitkov, published a paper describing something they thought might theoretically exist. Take a red supergiant, one of the largest types of stars in the cosmos, with a radius so vast it could swallow 1 billion of our suns. Now take a neutron star, the crushed city-sized remnant left behind after a massive star explodes. Pack them into a binary system close enough that one eventually swallows the other. The result, Thorne and Jitkoff predicted, would be a single star with a neutron star beating at its core like a second heart. From the outside, it would look like an ordinary red supergiant. But the chemistry would be wrong. Wildly, inexplicably wrong. Elements like rubidium, lithium, and molybdenum would show up in concentrations no normal star could produce, because the neutron star's crushing density would drive nuclear reactions that couldn't happen anywhere else. For nearly 40 years, nobody found one. Then in 2014, a team led by astronomer Emily Levesque announced they had located a candidate in the Small Magellanic Cloud, a dwarf galaxy about 200,000 light-years away. The star, called HV2112, showed exactly the chemical fingerprints Thorne and Jitkoff had predicted. Anomalous abundances of rubidium, lithium, and molybdenum sitting inside what otherwise looked like a regular red supergiant. The world of astronomy briefly lost its mind. Then in 2018, another team reanalyzed the data and disputed the finding. HV2112 might just be an asymptotic giant branch star, a different type of evolved red giant, rather than a true Thorne-Jitkoff object. The chemical signatures, they argued, weren't unusual enough to be definitive. So the first confirmed discovery evaporated. The objects remain unconfirmed. But here's the thing. Nobody is saying they don't exist. The physics is sound. Two stars in a close binary, with one exploding as a supernova, can absolutely result in a neutron star being kicked directly into the companion star's body. The orbital mechanics work. The nuclear physics works. The predicted chemistry is testable. There are dozens of red supergiant systems in our galaxy and nearby galaxies that astronomers are watching right now, looking for the signatures that would make one of them the first confirmed Thorne-Jitkoff object. A star with a collapsed, city-sized dead star as its engine. Still theoretical. Still being hunted. And if one is ever confirmed, it would open an entirely new chapter in our understanding of what stars can actually become. But neither of those two stars, not the impossibly old Methuselah, not the as-yet unconfirmed stellar cannibals, is the weirdest thing we've found in the night sky. That title belongs to a star 356 light-years away in the constellation Centaurus, officially cataloged as HD 101065. But named for the Polish astronomer who discovered its insanity in 1961, Przybylski's star. Its surface temperature is roughly 10,600 degrees Fahrenheit. Its mass is about 1.5 times our Sun's. On paper, nothing alarming. But the moment astronomers pointed a spectrograph at it and split its light into a spectrum, they knew they were looking at something that had no right to exist. A star's spectrum is its fingerprint. Every element produces a unique pattern of absorption lines. Dark bands at specific wavelengths where atoms absorb light. When you look at our sun, you see the fingerprints of hydrogen, helium, iron, calcium, sodium. Normal stuff. When you look at Przybylski's star, you see something that should be physically impossible. The spectrum contains the signatures of short-lived radioactive elements. Not just slightly radioactive elements. We're talking about actinides, the same family of elements as uranium and plutonium. Specifically, neptunium, plutonium, americium, curium, berkelium, californium, and einsteinium. Several of these elements have half-lives measured in decades or centuries. One of them, californium-252, has a half-life of about 2.6 years. This star is 1.5 billion years old. If californium-252 has been present since the star formed, it would have decayed into nothing 500 million half-lives ago. There should be zero. not a trace. Yet astronomers keep finding it in the spectrum, year after year after year. Where is it coming from? There are a few working hypotheses, and none of them are comfortable. One suggests that there's an undiscovered island of stability in nuclear physics, a region of the periodic table where superheavy elements with 114 or more protons can actually survive long-term, and that the actinides we're detecting are the slow decay products of these unknown stable elements. That would mean there are elements on the periodic table we don't know exist yet, silently breaking down inside this star. Another hypothesis involves atmospheric particle bombardment, creating nuclear reactions in the outer layers of the star on a continuous basis. Essentially, the star is manufacturing these elements constantly, replacing them as fast as they decay. A third explanation, rarely spoken aloud in polite astronomical circles, is that something extraordinary is happening on or near this star that we don't have a framework to describe. Przybylski's star has been studied for over 60 years. The mystery has not gotten smaller. It has gotten deeper. Now let's talk about what the universe has been showing us more recently. In 2024, astronomers working with the European Space Agency's Gaia satellite identified what is now the most massive stellar mass black hole ever found in the Milky Way. They named it Gaia BH3, and it weighs 33 times the mass of our Sun, sitting roughly 2,000 light-years away in the constellation Aquila. By itself, that's extraordinary. This kind of black hole had only ever been detected in other galaxies before. But the star orbiting it told an equally strange story. The companion star is an ancient giant, formed in the first 2 billion years after the Big Bang, carrying almost none of the heavy elements that stars like our Sun accumulate over billions of years. It's a ghost from the very earliest cosmos, still orbiting what was once its partner star. Now dead, collapsed, and quietly feeding off whatever drifts too close. The discovery forces a reckoning. If a star this ancient, this chemically primitive, formed as early as we're now calculating, then the very first stars must have been producing massive black holes sooner than our models predicted. The timeline compresses. The early universe was more violent, more fecund, more strange than we imagined. And then there's J0524-0336. In 2024, a team at the University of Florida announced they'd found a star roughly 30,000 light-years away, about 30 times the size of our Sun, carrying 100,000 times more lithium than our Sun contains. That number is not a typo. 100,000 times more lithium. Stars are supposed to burn lithium off as they age, trading lighter elements for heavier ones through nuclear fusion. The older a star gets, the less lithium it should have. J0524-0336 appears to be in a late phase of its life, and yet it is swimming in lithium at concentrations that no current stellar model can explain. The leading theory is that it caught what researchers are calling a lithium flash, a brief, violent, never-before-observed phase of stellar evolution that floods a star's outer layers with the element right before it dies. Brief, in stellar terms, means a few thousand years. We may have caught this star mid-flash. If so, it's the first time we've ever observed this phase directly, and we got lucky. In a few thousand years, the lithium will be gone, and the star will look like nothing remarkable at all. What all of these stars share, the two old Methuselah, the neutron star cannibals, the radioactive mystery of Przybylski, the primordial giant orbiting a dead companion, the lithium-saturated giant mid-transformation, is a refusal to behave the way our models say they should. And that is not a failure of the stars. That's an instruction. Every time a star breaks our model, it's telling us our model is incomplete. The universe doesn't care about our equations. It was here for 13.8 billion years before we started writing them down, and it will be here long after our most sophisticated telescopes are dust. Every anomaly is a signal. Every impossible star is a door. The history of astronomy is the history of being wrong in productive ways. We thought the Earth was the center of everything. We thought the Milky Way was the entire universe. We thought stars were holes in a celestial sphere. Every time we encountered something that didn't fit, we didn't discard the universe. We rebuilt our understanding of it. Right now, the Hubble tension has two sets of measurements giving two different answers for how fast the universe is expanding. Right now, Przybylski's star is producing elements that should have vanished over 1 billion years ago. Right now, there are stellar mass black holes in our own galaxy that only exist, according to our previous models, in galaxies billions of light years away. Something is slightly off in our picture of the cosmos. We don't know exactly what, but the stars themselves are pointing to the answer, one impossible measurement at a time. Here's what I keep coming back to. Every one of these stars has been visible for years, some of them for decades. HD 140283 has been in our catalog since 1900. Przybylski's star since 1961. The math didn't break until we got precise enough to see the break. Until our instruments were sharp enough to catch the universe telling us something we weren't ready to hear. Which makes me wonder, what are the stars we can't measure precisely enough yet? What anomalies are hiding inside the 300 billion other stars in this galaxy, waiting for a telescope sensitive enough to expose them? What is the universe trying to tell us that we're still too deaf to hear? So here's the question I want you to sit with. If a single nearby star can expose a tension in the entire timeline of the universe, what does that say about how much we think we know versus how much we actually know? Drop your answer in the comments. I genuinely want to hear what you think. If this blew your mind even a little, hit the like button and share it with someone who needs to spend the next 15 minutes questioning everything they learned about space. And make sure you subscribe, because next week we are going inside the most violent events in the known universe. Explosions so powerful they briefly outshine entire galaxies, and they've been happening closer to us than anyone expected.